Coil shocks? Air shocks? What's the difference? And does it matter? This is MTB Suspension Science Episode 1, Coil versus Air Shocks. Now, the main difference between coil shocks and air shocks is how the amount of force required to move the shock changes throughout its stroke. Coil shocks are linear and air shocks are progressive. But why? Let's talk about that. Let's start with the simplest of the two, the coil shock. Now, coil shocks are considered a linear shock. What does that mean? Coil shocks use a coil spring, which is characterized by Hooke's law, F equals Kx. And in our application, F is equal to the force required to move the shock, K is the spring constant, and X is the amount the shock has been compressed from its equilibrium, or in our case, the amount the shock has moved through its stroke. So, as the shock moves through its compression, X increases, and thus the amount of force required to move that shock further into its compression also increases. You can see that play out on this graph, where the relationship between the force required to move the shock and the distance into the shock stroke is completely linear. You get a nice straight line. Right here at 0, you have 0 force. But all the way into 3 inches of compression, or 3 inches into the shock stroke, you get 1,500 pounds of force required to move. And that's for a 500 pound per inch spring constant. Now, there are some companies that can make a slightly progressive curve for their coil shocks. You can run a progressive coil spring, which is what I run on my bike, where it has a 450 to 550 pound per inch spring rate. Or you can have a company like EXT, which uses a hydraulic bottom out circuit in the last little bit of the suspension travel to make a slightly progressive curve on this graph, even though they're using a coil shock. But for the most part, coil shock is completely linear. The relationship between the force required to move the shock and the distance into the travel is a linear relationship. In contrast, air shocks are progressive by nature. And this is due to the inverse relationship between pressure and volume as the shock moves through its stroke. And that's represented by Boyle's law, where P1V1 equals P2V2. Now that means the initial pressure times the initial volume must equal the pressure times the volume at a situation where the shock is compressed. So why does that matter? Well, if a spring is characterized by a spring rate, and we know that the force required to move that spring is F equals Kx, in the simplest possible terms, an air spring is just basically a spring with a variable K value. Now, in actuality, it's a lot more complicated than that, and looking at the equations gets a little bit hard to dig into, but I did, so let's do this. Since we know that pressure has to increase as the shock compresses, we need a way to relate that pressure to the distance the shock has been compressed, or the distance the shock has moved into its stroke. So to start, we can look at this equation for the force felt from an air spring, which is F equals PA. Now, P is just the instantaneous pressure within that air chamber, and A is actually going to be the effective area. Now, if we're assuming a single acting pneumatic air spring, such as this diagram, that A becomes constant, and it is just equal to 1/4 pi times the diameter of the air chamber squared. This is just the cross-sectional area of that air chamber. And this is going to be consistent throughout the travel. And that's good news for us because now we can create an equation based off of this P. So we can go back to Boyle's law and we can solve for P2. And that gives us P2 is equal to P1 V1 over V2. Or P2 is equal to the initial pressure times the initial volume divided by the current volume. That current volume is equal to the cross-sectional area of the cylinder times the current height. And that current height is just the distance between the top of the piston and the bottom of the cylinder head. So we can equate that to H, the current height, is equal to little h, the initial height, minus x, where x is the distance the piston has traveled, or the distance the shock has been compressed. That same x that you see in F equals Kx. So now we can plug that all back into our initial equation of F equals PA, and we get F equals P1 V1 over A, H minus X, all times A. This can be greatly simplified to the initial pressure times the initial volume divided by the stroke length, the total stroke length, minus the distance the shock has been compressed. And that is something we can graph. So now putting that into a graph shows a very clear progressive relationship between the amount the shock is compressed and the amount of force felt at the shock. So what we have here is, if you assume about 180 PSI originally, you plug that in as your initial pressure, you can calculate the initial volume given your stroke length and your cross-sectional diameter. You plug that in, and then H is your stroke length, and you can plot it via X, and you get this. So this is what the plot of an air spring is going to look like. And you can see how much faster it ramps up in progressiveness versus just a straight line that you get with a coil. And the cool thing about air springs is you can fine-tune this. So in a coil spring, this is the line you get. You get a linear relationship, and you can change that by putting a heavier spring, and that just takes this linear line and shifts it up. On the other hand, air shocks are way more interesting. You can change that initial volume with volume spacers, and that means that this ramp-up rate is going to go even faster, and you can change the amount of pressure as well, which would move this whole shape up without changing the shape. So there's a lot more tuning you can do in an air shock, right? So whereas this one ramps up really fast at only maybe 2 inches of stroke, let's say if you have a bigger initial volume, then you can ramp this up a lot slower. And engineers can mess with this. They can mess with the volume, they can mess with the piston diameter, how much force is going to be perceived, and this is how you can really fine-tune an air shock versus a coil shock. So why does all of this matter? Well, coil shocks are great on a bike with a progressive leverage ratio, and they're really great for small bump sensitivity, but they can struggle with some bottom out resistance. And so sometimes in order to get that bottom out resistance without using a hydraulic bottom out circuit or a progressive coil spring, you have to go up in spring rate, which means you're going to lose some of that initial small bump sensitivity. And so that's where air springs come in. Air springs can be tuned to work on bikes with both a progressive leverage ratio and a linear leverage ratio, and they can be tuned to run for anything in between. They're extremely versatile, and that's where they're convenient. However, they lose some of that small bump sensitivity, and they lose the predictability. Ultimately, which is better comes down to preference, riding style, what bike you're on. It's really a lot of factors. So which would you choose? And did you learn anything today? Let me know in the comments below. And stay tuned for my next episode where I'm going to start talking about suspension kinematics and single pivots, linkage-driven single pivots, horse links, all that stuff, why it matters, what kind of shocks pair well with what kind of suspension design, and just get into the nitty-gritty and awesome world of mountain bike suspension.